Okay, now let's talk about how to calculate the potential difference in a series and parallel circuit. All right, so let's say for example, okay, let's say I have an EMF of 9 volt. Again, 9 volt equals to 9 joules of energy that's supplied to each coulomb of charge that passes through the cell. Okay, so if I have two light bulbs here and I connect them in series, so if this is a series circuit, it means that the electrons or the charges has only one path to flow together. Okay, so I want you to imagine 1 coulomb. Okay, so when 1 coulomb passes through the cell will give it 9 joules of energy, right? That's the meaning of 9 volt. So it will carry with it 9 joules, okay, all the way. Now, there is no energy loss in copper wires, or rather very negligible, so you don't have to consider it, okay? Now, take note that before it reaches the first light bulb, or before it goes through the first light bulb, it still has 9 joules. Now, the charge knows that there are 2 light bulbs ahead, so they will proportionate the, or rather they will distribute the energy equally, assuming they are the same type of light bulb. So for simplicity's sake, let's say that these 2 light bulbs are of the same type, same resistance. So I have 9 joules. So therefore, each coulomb will know that I will divide the energy. So the 1 coulomb that passes through the first light bulb will give it 4.5 joules of electrical energy for it to light up, which means that once it passes through the first light bulb, it no longer has 9 joules, but it will have 4.5 joules simply because he knows that there is another one up ahead. So as it passes through the second light bulb, it will give all of the 4.5 joules, which means that it has delivered all the energy and it will return home without any electrical energy. It will simply continue to move due to the EMF. Just like the water pump, the water will keep flowing, just like the EMF, just like how the EMF provides the energy, the charges will just keep flowing, okay? But this time around, they will be going back without any energy, okay? So they no longer carry energy. So therefore, if I were to place a voltmeter here between the first light bulb will show me that it will take 4.5 joules for every coulomb. So therefore, the potential difference here is 4.5 volt, okay? If I were to put another voltmeter to measure the energy difference, okay, between the charge before and after the light bulb, it will also show me 4.5 minus 0 will therefore give me 4.5 volt. Okay, so for a series circuit, the EMF of a cell will be equal to the sum of the individual potential difference. Okay, so let's give you another example. So the question may tell you that the EMF is 12 volt, and they tell you that the light bulb here and a resistor here. Okay, so this is a series circuit because the charges has only one path to go through. Okay, so questions will give you something like that. They will ask you, what is V1? What is the potential difference V1 if the potential difference across the unknown is 4 volt? Okay, so likewise, we use the formula here. The EMF, the total EMF is equals to the sum of the potential differences. Okay, so 12 volt is equals to V1 plus 4 volt. So therefore V1 equals to 8 volt or 8 joules per 1 coulomb. Okay, so this is how you solve when they are in series circuit. Okay, then you have to use this formula here. Now let's take a look at what happens if it is a parallel circuit. How do we calculate that? Okay, so let's say for example we have a parallel circuit. So again, let's say this is 12 volt and we have parallel circuit, meaning to say that I will have another alternative path where I will have a second light bulb. So there are two paths with which the charge can choose to take. We call this a parallel circuit. Okay, now assuming, let's imagine ourselves as a 1 coulomb. So 1 coulomb, as the delivery man passes through the cell, it will receive 12 joules from the EMF. So it will carry with it 12 joules. So each coulomb will carry 12 joules. Now, when it comes to this juncture, it can go through two paths. It either go through this path in red, okay, or the path in yellow. Okay, so there are two paths it can choose to take. So let's say, for example, the charge in red goes through the first path. So before it reaches the first bulb, it still has 12 joules. Now this charge here only has this light bulb in front of this charge before it goes back home. So it will deliver the entire 12 joules to this light bulb, okay? And it will return home without any electrical energy. So it will go back home with 0 joules. Okay, so if I were to put a voltmeter to measure the energy difference between the charge before and after, okay, so this is the potential difference. So the potential difference is really to measure the energy difference that the charge carries. So originally it was 12, after that it was 0. It tells me that 12 joules have been given to the light bulb for 1 coulomb. So this is 12 volt. Okay, now let's see if there is a charge, another charge that decides to take the yellow path. So instead of going through the first one, it goes through the second one. Again, it will carry 12 joules just before it reaches the light bulb. So again, there is only one light bulb in its path, so it will deliver the entire 12 joules to the light bulb, which means that once it leaves the light bulb, the coulomb will have 0 joules of electrical energy, and it will head back home with 0 joules of electrical energy. Okay, and it will go back home. Okay, so likewise, if I were to put a voltmeter to measure the energy difference or the potential difference across this light bulb, okay, so originally it is 12 joules. After that, each coulomb becomes 0 joules because all the 12 joules is given to the light bulb. It becomes 12 volt. Okay, so what you can observe is for a parallel circuit, the EMF will be equal to the total EMF in each path. Okay, so therefore the formula is the EMF will be equals to the total EMF across the first path will be equals to the total EMF across the second path, etc. So this is the relationship between EMF and potential difference in parallel circuits. Okay, so they will give you two types of example. Let's go through the simpler one first. A simpler one will look like this. So if it is 5 volt, they will ask you things like, if the EMF is 5 volt, okay, they say that this is, find out what is V1, what is the potential difference across the first light bulb, what is the potential difference across the second light bulb. Okay, so this is a simpler example. So you know that the EMF will be equal to V1 equals to V2. So therefore, they will all be 5 volt. Okay, now but a tougher example will be the one here. Okay, so again, if this is 5 volt, okay, but instead of having only one light bulb, I'll have 2 in the first path. Okay, so maybe let's change it to unknown resistor so that they would be different, and then a third light bulb, a second light bulb. Okay, so what you need to understand is the 5 volt, these two are in series. Okay, these two are in series, so therefore these two individual potential difference V1 and V2 will add up to give you 5 volt, which means that this entire thing, the potential difference across these two will be 5 volt and not individually, and this will be 5 volt. Okay, so this is how you understand that EMF is equivalent to the potential difference for that branch, and if that branch has 2, then the sum of these two will give you 5 volt. Okay, so if this is 3 volt, this must be 2 volt, all right, and the third path. So I hope this clarifies some of the misconception.